So I modified these slides a little bit. I added some video. I thought that was interesting. And so these video slides, there are two of them, won't be on the slide deck that's up there. But then again, for a slide deck, you don't have video. I can certainly post a URL to the videos on the slides that are on the Blackboard sites for both the grad class and the undergrad class. So the homework, or rather the project, as I'd posted on the Slack channel, I am dropping the extra questions. And so for the homework project, I mean, you'll just be doing the Wireshark assignment, but not the extra questions that had the experiments pertaining to 4A through E. And so has everyone already done the Wireshark part? Not the extra? Who hasn't? Don't be embarrassed. All right. So that's about half. So what I'll do is I'll extend it another, I can't afford 2 days. If I'll extend it another day, right, to give people an opportunity because I do recognize that I had said I was going to change up the extra part and then give you extra time. So I can imagine some people said, "Hey, all right, he's going to change it, so I have some extra time." So to be fair, I'll give you an extra day, and I'll update the Blackboard after this class to reflect that as well as the assignment PDF. Okay. All right. Any questions about where we left off about the assignment? Okay. And so if you are on Mac OS or Linux, you're going to have to make sure that the device file for your network card gives you the permissions to access it. It does it with a Wireshark installation, but on Unix, you might need to change permissions manually. Is anyone running Linux? No? Okay. All right. That's a moot point then. All right. So why don't we get started? So where we left off, what clicker works? Yeah, project one. When we left off, we talked about packet switches in general, and we said these things are store and forward devices. And I really like this figure because it illustrates very precisely what's going on. And so a packet is a unit of data, and a packet for IP version 4 is typically 4096 bytes long. And so when that packet is being transmitted across the wire, or wireless, depending on what your communication link is, it's transmitted or encoded one a bit at a time. And so as it's reading top to bottom, left to right, all of the bits that comprise your packet, some of that packet will be at the sender side, while some of that packet is in flight over your communication link, while some of your packet is at the destination endpoint on the other side of that link. And so here we have a host on the left-hand side. We have another host on the right-hand side. And the host on the left is connected to a packet switch in the center through communication link that traffics in data at R many bits per second. And it doesn't matter what R is. And please note that's B with a lowercase b, so that's bits per second. Whereas if it were capital B, it would be bytes per second. That's really, really important to pay attention to. So here we have a packet that's being transmitted. And you'll notice here that empty part, you can almost think of it like as a fluid. That empty part are those bits that have been transmitted across the wire. And as they're transmitted, they're received at the other endpoint on the other side of that communication link, and it reconstructs that packet one bit at a time. So in this particular case, half of it has been transmitted, and the other half is still yet to be transmitted. And so you can imagine this packet is sort of straddling both sides of that communication link. Some of it is still at the sender side, yet to be transmitted, and the other part is at the receiver side. And so to be a receiver, you need to have some storage. You need to have some buffer, some memory, and that memory is used to store that packet both in when it's in flight, meaning while it's still being transmitted, but also those packets that are waiting to be transmitted out on the outbound side of this packet switch. And we'll talk a little bit more about that specifically. So you can imagine more than one packet at a time is being transmitted. They wait in line, they queue. So there's a data structure involved, a queue. And outbound packets are queued, bless you. And as packets are received at your packet switch, that packet switch analyzes information in that packet and then decides which link to forward it. Now, in this particular case, we only have one link going out from this packet switch, and really you could consider it as two links, right? If you're going from right to left or left to right, but you can have, imagine another link coming out here going down. And in that case, when a packet comes inbound from the left-hand host, it's analyzed, and based on that analysis, and we'll talk more specifically about that analysis in subsequent modules, but based on that analysis, it'll either send it out this link or the other link. And so the address, which we'll talk about much later, will determine whether or not it goes out one link or the other link. And so where we left off, we talked about the delay, right? And we said that if it takes, if the transmission link or the link has a bandwidth of r bits per second, and our packet is of size L many bits, then we just divide. We say L over R, the units are seconds, and that's going to be the number of seconds it takes to transmit that L-sized packet over that link that transmits at a bandwidth of R bits per second. And so if we were to look at the units, we have L in bits, and we have R divided by R, that's in bits per second. I'm hearing Tansy in my other ear. That's weird. Especially when you go in that corner of the room. But nonetheless, you have L and the units are bits. You have R and the units are bits per second. And so if we were to take a look at this, we have bits over seconds, and we have something in the denominator here like this. So that's going to flip, and our units are going to be bits over second here, and we have bits here, right? So if you were to take that bits over 1 second over bits, right? So this fraction here in the denominator, it flips when you have a fraction in the denominator. And so the bits cancel, and we're left with a unit of seconds, right? So it'll be really, really important to make sure that you're keeping track of the units, right? And so if a problem states that something is in bytes, you have to convert it to bits, right? 1 byte is 8 bits, okay? All right, any questions about this? And so the example given in the book gave 7.5 megabits as the size of the packet. So L is 7.5 megabit, and R is 1.5 megabits per second. So you notice here another abbreviation. They don't say bits over seconds. They say Mbps, right? P per, you could think of it as that line there representing bits per second, okay? All right, so if we divide 7.5 by 1.5, again, the units are seconds, and that divides 5 many times, so we get a delay of 5 seconds for that link. Now, that's just one of the links. So if it takes 5 seconds to transmit across this link, well, when it forwards, we have the same transmission rate for the second link. That also, it's because it's R many bits per second. If R is 1.5, it's also going to take 5 seconds to transmit that packet across the second link. So for a single packet, that means 5 seconds for the first hop, or the first length of communication link, 5 seconds for the second hop. So if we were to ask the question, what is the end-to-end transmission delay, right? That's from the source machine, that's on the left-hand side, to the destination machine here. End-to-end implies your packet is going to traverse every single communication link, every single hop that you need in order to get from the source to the ultimate destination. Does that make sense? Any questions? So for that reason, we have 2 times L over R as the so-called end-to-end delay for this particular case. All right, so it's really, really important to make an accounting both for the units as well as all of the hops going from source to destination. Okay, all right. So let's continue on, and let's talk about queuing. Now, of course, more than one packet is going to come into a packet switch at any given time. And that might be because you have a really fast burst of packets coming from one machine across a link, or it could be because you have multiple machines both sending or all sending packets to the same packet switch. Now, in that particular case, it's conceivable you're going to have packets coming into that packet switch faster than that packet switch can transmit them on some particular outgoing link. Now, in that case, if you have more going in than going out, well, you have to store them someplace. And that someplace where they're stored is a buffer, or more specifically, it's a queue. And so typically, these packets will arrive in some order in time, and they'll line up in the queue where the head of queue packet is the one that gets transmitted by that router. Now, that transmission it doesn't just get sent out, it's analyzed. And that analysis takes time. And while that analysis takes time, as more packets come into the packet switch, they line up in this queue. So you might ask yourself, what happens if I run out of space? That's a great question. And you can, in fact, run out of space. The only decision or the only course of action the packet switch can take in that regard, or in that case, is that it has to drop that packet. And so to you, when you're, say, streaming some music or watching a video or doing a Skype chat, when that packet gets dropped, one of two things can happen. Either your communication end to end says, I'm going to ignore it, and you perceive that as like your video's a little choppy or it sort of skips a frame or the music kind of something skips, or your endpoints, the sender and receiver, say, well, it didn't get sent, let's resend it because it was dropped along the way because somewhere in a packet switch from the source to the destination, it ran out of buffer space or queue space and it had to drop that packet. So in the case where it does not drop the packet, recall they still line up. So if it takes time to process the head of queue packet to transmit it across an outgoing link, well, that means the others have to wait. And the consequence of that waiting is so-called delay. And what that delay, how you perceive that delay end-to-end in your network application is that the thing is slow, right? And so sometimes people will say the network is congested, it's stuffed up, kind of like human congestion, right? When you have a cold, that there's packets sitting there in the queues waiting. And so the end-to-end communication, the perception end-to-end, is that this thing is slower. And that does, in fact, impact the performance end-to-end. And so here, when we have our packet switches, if the arrival rate for the packets on the inbound links exceeds the transmission rate for a period of time, the packets are going to queue because they're going to wait for their turn to be transmitted out some outgoing link. And of course, if memory fills up, well, you have to drop a packet. Now, there are schemes that I'm not telling you about, but the dropping the packet doesn't happen to the last one in line that sees a full buffer. Depending on the level of service you purchase, there might be a decision made to say, okay, well, every packet is stamped with some encoding of whether you buy, the bronze plan, the silver plan, or the gold plan. Right? You pay more money. What you're paying for is quality of service guarantees, and how that can sometimes take implementation in the route infrastructure or the packet switch infrastructure is that if it's going to make a decision to drop a packet, if a newly arriving packet sees a buffer or a queue that's full, it says, I'm going to drop one of those packets associated with the bronze plan, because the others are paying more. They are not the premium customers, so to speak. So when I'm going to choose a packet to drop, I'm going to choose one associated with the non-premium customers. Okay, and so the result of that is that if you pay more for these service guarantees, your flow or your end-to-end performance is going to seem faster because it's less likely that your packet is going to be dropped should there be packet loss in the routers or packet switches along the way between the source and the destination endpoints. Okay, any questions about that? Does that make sense? Yeah? All right. So what happens inside of this packet switch? Now, we said it's a store and forward device. Now, how does this forwarding happen, right? We talked this more generally about this idea of an address, but I'm just going to kind of hand wave and say address more generally until we get to the network layer. We'll talk about ad nauseum, what the structure is, and what these decisions really are. But at this juncture in the course, we're just kind of taking inventory at a high level of what all the pieces are and how they interact with one another before we dive deeper into the details of each of these components. So in a typical packet switch, more specifically a router, it performs what's called storing and forwarding, right? And so inside every router are two major components, the routing algorithm and what's called a local forwarding table. Now, the local forwarding table, it has a bunch of numbers in it, and these numbers in binary represent addresses. So when your browser says, I want to send this message to that machine, it uses this address. And the binary representation of that address is checked against each of the entries in this local forwarding table in this column called header value. And then you'll notice here, associated with each header value is a numbered output link. And so if the address destined for which your packet is destined, and every packet is stamped with an address, if the destination address that's stamped on that packet falls within a certain range of values, the router or the packet switch is going to forward that out a particular link. So in this particular example, we have some link here, and there's a packet coming in, and it has a destination address, a header value, and it comes in, and you'll notice here the other links on the router are labeled 1, 2, and 3, right? And so in this case, this particular packet is stamped with 0111, and we see a 0111 there. It matches that particular entry in the forwarding table, and it says if you have a 0111 in your address and some prefix or suffix, which we'll talk about later, forward it or send it or transmit it out link number 2. So then it would take this packet, it'd perform the analysis, and then transmit it out link number 2, 1 bit at a time. Okay? All right. The other part of this router, this packet switch, is a so-called routing algorithm. And you notice here, routers are connected to one another through some link, right? And this routing algorithm is a process, and it runs in the background on the router. And there's nothing special about a router. A router is just a machine, right? You can set up your laptop as a router, or you could buy a very expensive router that's highly tuned for this function and therefore very high throughput. But nonetheless, your packet switch, or specifically router, runs a routing algorithm, and this routing algorithm contacts other routing algorithms on routers that are nearby. Now, this definition of nearby means that you are connected through an edge. So this router on the extreme right would contact the router next to it here, through a link there, through a link there, and they exchange information. Now, that information exchange, when we talk about the network layer, and more specifically about routing algorithms, has to do with the amount of traffic or how much bandwidth is used up on the link that's shared between the routers that are exchanging information. And they use that information in aggregate to try to find or calculate what is the best path to get from some source router to some destination router. Okay? And so inside every packet switch are two major components: the local forwarding table, which makes this decision about out which link a packet should be transmitted. And then it also has a routing algorithm, which more globally determines what is the right sequence of paths to try to minimize the time it takes to send between some destination and some receiver endpoint. Okay. Any questions about this? Does that make sense? Yeah. Okay. So there are two key functions for what's inside of these packet switches. There's the routing and there's the forwarding. Okay. And so when we establish pathways, there are two major ways to do this. It's called packet switching and so-called circuit switching. Now, circuit switching kind of goes back to the original setup of the phone system. Now, this is before my time, but reading stuff, and I look up that in the earlier days of telephone communication, you would dial the local operator and you'd say, "Connect me to such and such number," and this person would take like an audio jack, unplug it, and then plug in physically someplace else to set up the call for you to talk to someone. And so this idea of so-called circuit switching is the idea of reserving a circuit or a pathway, conductive path, along which you can send information. And it's similar to how the operator would take an audio plug and plug it into a port somewhere that was establishing a physical electrical connection between the wire that came from your phone into the central office to some other line that connected you to another phone. Right? But that was very, very early in the history of the phone system. And so they kept a similar sort of thing as it started to modernize and became computer controlled. They have circuit switching under computer control, where instead of an operator, it's a computer establishing these digital pathways. So in this particular example, we have 4 lines, and each line is a circuit or a pathway over which you can send information. And in order to do circuit switching, in order to establish a pathway, say from this source machine to that destination machine, you have to reserve pathways or circuits between every 2 components along the way. And so this requires what's called call setup. And call setup is the signaling between the packet switches, or the circuit switches in this case, to say reserve one of these circuits for this particular purpose. And so in this example, going from the source in the upper left hand, your left, to the lower right corner, we reserve the second circuit here, right? So that's the first, second, third, fourth, the second circuit on this path, and then we reserve the first circuit on that path to give you that connection. Now, there are some benefits and some drawbacks with circuit switching, and that's something you'll find with just about every aspect of computer networking, that there's no one right approach. It all depends on what sort of performance characteristics you want out of the end-to-end communication. So with this circuit switching, when you reserve a circuit pathway from source to destination, you have full use, dedicated to you, you have full use of this communication medium, right? That particular circuit. In similar fashion, if you have a copper wire and you're going to pass an electrical signal down that wire, you have full use of that wire's ability to transmit that signal until you now make it available for others to use. And so once you do this call setup, you're reserving these circuits, which collectively give you a pathway to send over which to send information between the source and destination. And one of the benefits here is that you have guaranteed bandwidth. You have full use of this available bandwidth. Now that's both a benefit and a drawback, because if you choose not to use all of that bandwidth, it goes wasted. So let's say you have a circuit switching network, and they still exist today, and you decide that you're just going to send maybe 5 bits per second, right? And let's say this thing can incorporate 1 megabit per second, but you're only using 5 bits per second. The remainder that you're not using goes unused, and it's just wasted, right? Now, there are applications where you absolutely want guaranteed bandwidth. If you're doing like robotic surgery, right? You want to make sure you have precise control over that robot mechanism, and you don't want to know that all of a sudden, your robot doesn't behave reliably because somebody decided to watch Game of Thrones on YouTube, right? Congesting the network. Your packets are dropped because somebody's watching or playing video games. So for certain applications, dedicated bandwidth is important, but for other applications, that might not be your best idea. Okay? So each link has 4 circuits. It's dedicated resources, so you're not sharing any bandwidth, which is what happens with packet switching, which I'll talk about in a slide or two. And it remains idle if you don't use it. There's no sharing. And so this is used in telephone networks, but there are specialized applications where it's important to have this circuit-like behavior. Okay. Any questions about this? All right. So how is circuit switching performed? Right. So does anyone listen to regular radio? Still? No? Oh, like streaming? Okay. So on regular radio, right, you have electromagnetic spectrum, as it's called. And, when you listen to, say, 105.3 WDAS or 88.7, which is the bridge, that number represents a frequency, right? And that frequency connotes or stands for the center frequency in a band or block of frequencies over which information, namely the audio for the radio signal, is being passed. Now, of course, you have many different frequencies that you can use, and the frequency is carved up into blocks, and that set of blocks are called the frequency spectrum. And so how you get circuit switching, there are 2 different ways you can do it. One is called frequency division multiplexing, and one's called time division multiplexing. To multiplex is to have multiple uses for the same object. So let's take a look at so-called, frequency division multiplexing. Now, in time, you're going to send data, right? 1 second, 2 seconds, the next second, the next second, the next second. But then you have this frequency spectrum, which describes a block of frequencies over which you can send data. TV works the same way. When you change to a channel, what you're doing is you're setting your TV tuner to pick out that block of frequencies. And in the case of something like cable TV or air TV, what you're doing is picking out information for a particular part of the spectrum, a block of frequencies, and getting that audio and that video data. Okay, so here on the horizontal axis we have time, and on the vertical axis we have frequency. So you can imagine this frequency, if we have 4 different users of a network, it's chopped up into 4 blocks. So maybe this might be from 10 to 20 megahertz, and that might be from 20 megahertz to 40 megahertz, and that might be from 40 megahertz to 60 megahertz, and so forth. You have a block of frequencies over which you can send data. So now, each of these users is now allocated a block of frequencies. The purple, the green, is that purple? No, that's blue. The blue, the green, the looks like yellow, and the purple user. And then you can send data down each of these blocks of frequency spectrum the same way that a radio station or a cable TV provider can send their data down their particular allocated blocks of spectrum. There's also so-called time division multiplexing. And with time division multiplexing, each user of the channel has full use of all of the frequency blocks comprising the spectrum. And here we have time along the horizontal axis, and here we have frequency on the vertical axis. And this idea of time division multiplexing is that each user gets some allocation of some delta t, some bit of time, one after the other after the other. And so let's say you have 4 users. It's the first person's 10 milliseconds to use the channel, and then it's the second person's 10 milliseconds, it's the third person's 10 milliseconds, it's the fourth person, and then you go back to the first person again. It's exactly round robin scheduling, like you may have studied in operating systems. And so here we divide up time into epochs, and then each user, round robin, has usage of one of these periods of time. And so for circuit switching, underneath the covers, when you allocate a circuit, what you're doing in frequency division multiplexing, or FDM, is you're assigning some block of spectrum to each communication. And then when you say, I'm done with the communication, it's now made available for someone else to reserve. With time division multiplexing, or TDM, you're taking some delta t worth of time and you're assigning it to a particular user's usage. Now, when you're doing TDM, or time division multiplexing, each person for that delta t has full use of the whole spectrum. Which is better? It depends on what you're trying to accomplish. Okay. Any questions? No? So then you just send your data either using a particular channel or block of frequencies, or using a particular time slot if you're using TDM. Okay. And so when you reserve in circuit switching, you're reserving either a time slot or reserving a channel. Okay. So let's look at the alternative, which is what most computer networks use. You can still get circuit switching, but for the most part, general purpose, as well as some specialized, use so-called packet switching. And you can think of packet switching as a kind of statistical sharing, right? So in packet switching, the example given in the book is, let's suppose that you have a 1 megabit per second link, and that's the outgoing link from your packet switch. And let's say you have some number of users, n, and each of these n many users is pushing data into the packet switch. And so the assumption is that each user, when he or she is active, so that means you're actually sending data versus just sitting idle. So for example, if you're doing instant messaging, right, you type something, you're not sending data when you're typing. You hit enter, that data is sent, and then the person on the other end sees that message, and he or she is reading that message. You're not sending any data when that person is reading your message. When I say sending, I mean actually physically transmitting data across the wire. So when each user is active, the users each send 100 kilobit per second. Now, kilo is 10 to the 3. That's 1,000, right? It's also going to be very important for these problems to make sure you understand your metric units, okay? All right. So when active, each user sends 100 kilobit per second. And now each user, to add another wrench into this problem, is only active 10% of the time. So what does that mean? That means with a 10% probability, each user is going to be sending or receiving something. How do you measure something like that in practical terms? Well, you set a stopwatch, and then you say, okay, well, let's say every minute or every hour or every 15 minutes or what have you, what percentage of that time is somebody actually physically sending data? It's absolutely a measurement that you could take in an experiment. So each user, when active, sends 100 kilobits, 10 to the 3. So that's 100 times 10 to the 3 bits per second. And each user is only active 10% of the time. Okay, so circuit switching. If you have a capacity of sending from your packet switch of 1 megabit per second, right, and each user can send at 100 kilobit per second, if you're using circuit switching, what do? You reserve a channel. right? Now, again, if you reserve a channel, that fractional use of the channel is exclusively yours, whether you use it or you don't use it. So that means each of these users, if they want to send using circuit switching, they have to reserve a channel, right? And that reservation is exclusive, meaning that they're the only ones who can use that fractional bandwidth. So that means, given the specification of the outgoing link from the packet switch, if each user could potentially send 100 kilobit per second, now it doesn't matter if it's 10% of the time they're active. What matters is that, gosh, well, they could be using it, so they reserve enough bandwidth for their 100 kilobit, even though 90% of the time they're not going to be using it, right? So that's a lot of wasted bandwidth. But nonetheless, in that scenario for circuit switching, this outgoing link can only afford 10 users to be active using circuit switching, right? Because if you reserve 10 users, right, for 10 users, each one can send 100 kilobits. 10 times 100 kilobit is 1 megabit, and you fully saturated the bandwidth on that link. Okay, does that make sense? So that's a consequence of using circuit switching to share this outgoing link among these n many users. So what happens with packet switching? Well, with packet switching, you have full usage of the available bandwidth. So if you're not sending a packet, you're not using any bandwidth. If you happen to send a lot of packets, you'll use as much bandwidth as there is available. Now, this is where I talked about statistical sharing comes into play. Now, if each user is only active 10% of the time, well, suppose you had a total of 35 users. Now, if you took the same 10 count that you got as the maximum for circuit switching, where you're doing exclusive reservation of bandwidth, of fractional bandwidth, well, if you took the same 10 users with packet switching, now you're saying, what is the probability that you're going to have all 10 users at the same time sending, right? And so with a total of 35 users, now you're dealing with probabilities, more specifically a binomial distribution, right? You could think of a binomial distribution as, because I don't assume everyone's taken stochastic, no, not everyone. If you have a coin, right, and that coin comes up heads if someone's using the channel, it's tails if they're not using the channel. Now let's assume the probability of heads was 10%. It's not a fair coin. And now the question you're asking, if I flip this coin 35 times, what is the probability that more than 10 people will be using, more than 10 flips will come up as heads, right? And that corresponds to this idea of more than 10 people using the channel or being active at the same time. And so how that works is that you end up with a really, really small probability, something like 4 10,000ths. So that means 4 times in every 10,000 usages of the network, you're going to get more than 10 people contending for bandwidth, right? And that's a pretty small number. And so what that means is that using statistical sharing, you can support many more users because you're relying on the fact that at any given moment in time, it's a very low probability that you're going to have a lot of users sending and receiving at the same time. Now, if you're doing something like media streaming, it's a little bit different, right? But even still, some might pause the video, some might decide to stop the video, and so forth. Okay? Any questions about this? Does that make sense? Okay. And so it even gets better if you go to 35 users, right? The likelihood of 35 users, each with a 10% chance of using the channel at any particular time, the probability diminishes almost to zero. So it's a very rare event. Okay? And so the statistical sharing, what it does, it allows you to use the same bandwidth on the outgoing link among a larger number of users. With circuit switching, you get these bandwidth guarantees, but the drawback of that bandwidth guarantee, because there's a cost you pay for everything in networking, the drawback is that because it's exclusive reservation of bandwidth, it's not usable by someone else if you're not using it. Whereas with packet switching, the statistical sharing, you have full uses of bandwidth if no one else is using it. It's kind of like if you're ever on campus during a break and you use the network, it's really, really fast because there aren't that many people contending for the same bandwidth. Okay, so is packet switching the winner? Well, you might think, yes, it is the winner, and it's very good for so-called bursty data. Bursty data is data that can, it comes in at a certain rate, but every once in a while it spikes. Every once in a while it spikes. And the sheer fact that it spikes every once in a while, because it's statistical sharing, it'll absorb more bandwidth or take up more bandwidth momentarily, right? And so this idea of statistical sharing is great when you have bursty data. The other benefit of having this packet switching, this so-called statistical sharing, is that you don't have to do any call setup. You don't need to do any special signaling and coordination and reservation of resources, i.e. this fractional bandwidth along the circuits. And so it's simpler, and in any sort of engineering application, if you can simplify something, you can make it much faster and much more efficient because you have fewer assumptions in the code that drives the whole process. And so if you have a lot of congestion, meaning a lot of packets lining up in router queues causing things to slow down, of course you're going to have some issues with packet switching. And so there's this delicate balance when you design a network to choose the routers wisely, because it's not just the speed of the links that impact your flows from endpoint to endpoint. It's also the amount of queuing memory that you have or buffer space you have in the router. Now, of course, when you buy a router, all things being equal, if the switching speed is the same, the increased costs, you pay more if it has more buffer space in a particular router. Now, when I say routers, I mean enterprise routers. I mean things that'll cost you, 30, 40, 80, $120,000 that would switch something like half the campus in terms of pushing data on and off of the network. Okay, so it's ongoing research to try to get circuit-like behavior out of a packet switch, out of statistical. And the sheer reason that it's based on probability, it's really hard to implement this idea of reserved bandwidth. And that's an open question. I encourage you to go to grad school, get a PhD, solve it. You will be famous in the industry. Okay. Any questions about this? No? All right. So you can think of human examples. If you go to a coffee shop and you ask to use the bathroom, they give you that key that you can use to lock it. It's yours exclusively. If you go to a buffet, you're resource sharing. And so circuit switching is like using a bathroom in a restaurant where you lock the door and it's your bathroom for exclusive usage. Whether you actually use the bathroom or not, no one else can use that resource. Whereas you go to a buffet, everyone comes in line and they grab food and it's on demand. If you use more, you use more. If you use less, you use less. But it's this statistical sharing. Okay, so the internet structure is called internet because it's a network of networks. And we talked about this idea of an access network. And an access network is provided through a connection through an internet service provider or an ISP. Now, this could be residential, your Xfinities from Comcast or your Fios from Verizon and so forth, or it can be through a university, or it could be some enterprise provider, right? But everybody has an access network provider. And so any two hosts on the internet can send to one another, and that begets the fact that you need to have a connection among these ISPs if you want to get one packet from a particular access network to ultimately get to another machine that's served by another access network internet service provider. And so this resulting network, this interconnected set of networks facilitated through the access providers and also the global ISPs can get very, very complex. And so these interconnections between service providers, there are technical reasons, but more so it's a lot of agreements, human reasons. And they don't just do it out of the goodness of their heart when they share data flowing across the networks. It's based on money and other agreements. And so let's, in the book, and this is from the book, they take an incremental approach of explaining the connectivity of various entities that collectively comprise the internet backbone. Okay, so here we have lots and lots of access network providers. And these are ISPs that you would contact to provide a link to your home, to the university, to a company, and so forth. And there are many, many millions of these. And the question you might ask is, how do you connect them to one another? Because some machine hanging off this access network should be able to send a packet to any other machine that's hanging off any other access network. So you might think, okay, well, maybe I connect every access ISP to every other access ISP. So that, it turns into a little bit of a mess, right? And it's not feasible. If you have n many access providers, like a million, you'd have on order of n squared, so a million squared. So that's 1 times 10 to the 12 zeros, right? That's a pretty big number, and that's a lot of links. Would that work? Most likely not. It would never work. So certainly you have these other bigger service providers, and we talked about global internet service providers, and these global ISPs typically traffic in larger volumes of data, right? And so these access ISPs would be customers of the global ISP. Now that's a pretty good business to be in, right? Because you make a lot of money, and there's nothing precluding you in a home to actually subscribe to a link from a global ISP, but you have to be willing to buy, gigabits worth of data and pay whatever that cost is. They're not going to sell you a 50 megabit upstream downstream connection if you talk to a global ISP for service. They want to sell you big pipes to push lots of data, right? They don't deal with small data. That's more the domain of the access network. Okay, so if this is a great business, certainly, competition being what it is, a lot of people would want to get in on the action. So there are many, very many purveyors that manage and run global scope ISPs. Now, these global scope ISPs or national scope, they have to be interconnected because, again, you still have to get traffic or packets that are on this access network to ultimately get to any other access network across the internet. So these regional and global ISPs, they create connections. So data from ISP-C would get pushed to ISP-B, and likewise ISP-B to ISP-A, and vice versa. Now, of course, when you push data or pull data, that relates or translates to money, right? You have to hire staff to manage these machines. You have to pay for the electricity. You have to pay for the building in which these things are housed. You have to buy the equipment. So they're not going to do it for free. Sometimes they have these agreements where they say, okay, I'll take a gigabit of your data, gigabit per second of your data, if you'll take a gigabit per second of my data. Other times it's a monetary agreement. I'm going to have to pay you a monthly rate in order to send data onto your network, right? Without that, you don't get email from here getting to there. You don't get Skype sessions between two arbitrary machines on different endpoints of the network. Does that make sense? Any questions about this? So these connections are called peering links, and these peering links are facilitated by something called IXPs or Internet Exchange Points. And these are nothing more than server rooms with rack-mounted units where you have switches and you have cabling that goes physically from one machine to another machine, only the two machines belong to different internet service providers. Okay. So you might also have something that's in between the access network and the global ISP because maybe they don't want to buy that big of a data pipe, if you will, or rent one from the global ISP. They might want something a little bit lower bandwidth. And so what has developed are so-called regional networks, things that might serve, say, a greater metropolitan area like Chicago, or perhaps the Mid-Atlantic or the greater DC, Baltimore, Virginia area. New York City would probably be its own regional ISP because of the sheer density and level of population. But nonetheless, you're going to have regional networks that serve more localized needs beyond what the global ISPs might be interested in providing. So then you also have content providers, folks like Disney, like Netflix, like Microsoft, like Google. Now these organizations traffic in a lot of data, and of course you could say, gosh, well, why don't they just sign up with the global ISP and get a really big pipe over which to send data? Well, if they do that, they're going to be paying money. And when you have something that's core to your business, you don't want to trust that to someone else's whims. And what I mean by that is suppose all of a sudden, let's say Microsoft or Google for Gmail, they decided to subscribe to AT&T Global ISP organization, and AT&T decides to raise their rates. All of a sudden, Google's prices goes up. That's not stable, right, as a business. And so often these large content providers on a national scale, they build their own networks so that they own sort of their destiny, if you will, things that are integral to the underlying cost structure and reliability of that key service. And so these content providers will often straddle this infrastructure and act as their own global ISPs and regional ISPs. Now, you've probably read or maybe heard about something called Google Fiber, right? Google was offering a fiber optic high-speed internet in various metropolitan areas. And the reason why they're able to do that is because they're a content provider and they have this infrastructure already. So they said, gosh, well, why don't we get into the internet service provider business? right? But they don't have the same level of presence in every single location. So they chose more major metropolitan areas because it's easy. All right. Any questions about this? Does that make sense? So if it looks like a mess, yes, it is a mess. You have a lot of moving parts that interact, and the goal of the course is for you to understand these parts, but more importantly, the physics of networks. And by that, I mean if you make certain choices for certain pieces of the network, what does that give rise to in terms of the performance and the capabilities of the resulting end-to-end connection, right? That's really, really important to have mastery with. Okay, so this is a more of a hierarchical view of what this internet looks like. At the top, we have so-called tier one ISPs. These are the ISPs that are very global in scope, right? They traffic in many gigabits and terabits of information, and they push this data maybe over, half the length distance of the country from east to west, or the whole thing between countries, and so forth. And then you have these internet exchange points, IXPs, and these things are these special facilities where these organizations can share data, and they do that through trading of bandwidth as well as through money exchange. Then you also have your regional ISPs, and at the bottom you have your access ISPs. Now you might be wondering, how do some of these places make money? Like Sprint, I've been told, has not so good cell phone service, at least in this area, right? Well, Sprint has an enormous business as a global ISP, right? And all these companies, Verizon, Cogent, Level 3 Communications, they all run global ISP corporations. And so sometimes, there are companies that you hear about, but you never experience them yourself, and that's because they're not in the residential business. Now, at the bottom is the access ISP. Those are the Fios and Xfinity, and I know RCN and others run local access ISPs. And those are the ones, as a resident, that you're more likely to have heard the names. Okay. Now, are any questions about this? Nope. All right. So this, I think this is from 2015. This is a map of the United States for Sprint's Tier 1 or Global Scope ISP. Now, certainly this is not, this is obsolete for today, but it's just to give you an idea of what an ISP is, a Tier 1 ISP or global ISP is. And so they're not just covering the United States. The map only highlights the United States. At the time, I think it was 2015 when it was calculated or the data was collected. And so here we see a lot of links from various regions. And so, for example, if you go to Washington, D.C. area, you see a really broad link going from D.C. To the West Coast to Silicon Valley area, right? So as you can imagine, well, federal government, a lot of high bandwidth, a lot of companies, you're going to want really direct links to get to Silicon Valley because they do a lot of internet-related business. Okay, so you see a link from, where was it? I can't remember what it is. Seattle, there we go. Seattle, Washington, coming all the way down, lost it, to Kansas City, right? So coming from the Midwest where they have some finance, a lot of heavy industry and stuff like that. And Seattle has Microsoft and a bunch of other big companies. And so here we see these weird black diamonds over some of those dots. Those are called points of presence. A point of presence is a unit that's within an internet exchange point. And that's a physical data center where two different service providers have these peering links. So literally, you have data cables connecting packet switches that belong to different service providers. And this is roughly what it looks like. You have inbound and outbound traffic from customers. You have going out to the backbone, which are these high-speed, long-distance links coming into the backbone. And then you have these edges that go across from one organization's packet switch to another. Okay? All right. Any questions about this? No? All right. So these links, if you take a look here, you'll see that it's annotated global crossing, right? And so you wonder, gosh, well, what's going on there? Well, those are undersea cables. And those undersea cables are typically fiber optic communication because fiber optic has very little interference, but it can also transmit over longer distances. So let's take a little bit of a look at these global crossing type of links. And so in particular, I'm going to highlight CCOM, which goes around the continent, the African continent. But this is what undersea cable looks like. And sort of for scale's sake, you can see these workers here. They're adults, right? Human adults. And you can see how big that cable is. Now, this is an enormous spool, right? And this thing sits on a ship, right? And this cable, there's an example of the ship, and there's like another float chase vehicle, and you can see it trailing here with some buoys so they can know in what direction that cabling is going. And they literally lay it on the sea floor, right? More directly, more correctly, they dig a trench, and this trench, the cable is laid down in the trench, and it's actually pretty fascinating. They have this robot here, and this robot is an ROV, so it's a remotely controlled with a tether underwater robot. And so this robot has like what looks like a trowel, right? And it kind of cuts into the ground and has some high-speed water jets that kind of blast the sandy and rocky material, cutting a trench. And then it lays the cable down behind it into the trench. And then this little kind of skid takes the material that was dug up and buries this cable, right? And so it's kind of underneath the sea floor, buried in that sandy and rocky material of the sea floor. So this is an example as a scuba. This is probably nearer to shore because they don't scuba dive when they're out in the open ocean. But this is a picture of a scuba diver guiding some of this stuff, conceivably when they're coming closer to shore. And this is an example of what it looks like. And this is the ship, and this is a schematic describing the relationship between the spool ship, the trench ship, and the robot that lays the cabling. Okay, so and it's actually quite fascinating. Let me play a video that shows you a little bit, and I won't play the whole thing, of an actual trenching robot working on the sea floor. Now it's hard to see because there's a lot of, what looks like dust, this sand and debris floating around in the water. Um, so let me see if I can find another view. So there's the cabling, and the robot is moving, and it has some water jets, excuse me. And so the ship is out in front, lowering this cable under a guided lowering of the cable, and this robot is following along through a tether and is digging a trench, dropping the cable in the trench, or the cable is dropping into the trench, and then it gets covered by a skid, burying this thing in a trench. And that happens on the sea floor. You can imagine how deep the open ocean is when you even go like a mile or two offshore. Pretty fascinating stuff. Okay, so let's go to the next video. And this video, kind of go in the middle, um, shows you a cutaway view. They actually open up an undersea cable, what's inside of the plastic sheathing, which is that black rubber that has that yellow color banded around it. This is from a video. Let me see if I can. It's hard to hear. The sound is horrible. So, to the solstice, it should be going through the TV. No, pardon? Yeah, it was louder than the last one. Last one. Let me see. All right. Well, he cuts it. I'll just narrate. He cuts it, and not to sit here and spend 10 minutes watching it, but let me see. Yeah, I'm not going to mess with it. I'm not going to mess with it. Pardon? Oh, that's a good point. Volume. Ah, thank you. There we go. Oops. Ah. All right, let me see. I'm sorry. Let me do that. There we go. So all of that is just for what you're seeing in his hands, right? All of that is just for those, looks like maybe about half a dozen to a dozen uh, small glass strands that are painted with a resin. And all of that goes thousands of miles under the seafloor. And that cabling and the reinforced steel and the rubber sheathing and stuff is all for that, right? And as you'll see in the next slide, that traffics in quite a large volume of data, and it just says how efficient fiber optic strand is in giving you interference-free high-speed communication. Okay, so let's take a look at CCOM. This is a map of the internet infrastructure around the African continent, and you can imagine what this distance is. It's many thousands upon thousands of miles. And I know that Ghana is really, really hot as far as developing an AI machine learning infrastructure. And if you see here on the western coast, where's Accra? There's Accra, right? So if you look at this line here, the red, that red is 32 terabits per second. Can you even fathom 32 terabits? And you see trunk lines here leaving the western coast of Africa going out to Brazil, right? And another one going up in through London, throughout the Middle East and the Far East. Sri Lanka, right? This trunk here coming in from Somalia and Yemen area, 24 terabits going into Sri Lanka, right? So that's huge high-speed communication. And all of that is made through just maybe half a dozen to a dozen little glass strands, but in all that sheathing with the right signaling going through. Okay? All right. Any questions about this? And this figure is from 2018. I'm sure it's much bigger now than it was in 2018. Okay. Any questions? No? Make sense? So this is how these global ISPs do it. You might ask, why do they go through all that trouble to put things on the sea floor? Why don't you just send it to a satellite? That's a great question. Because satellites are very expensive and they're not very high bandwidth communication. You're using electromagnetic energy going through the atmosphere, right? And clouds have very high water content, and water is not a very good propagator of electromagnetic signals. If you ever, I don't know, anyone have a satellite dish for TV? Right? You ever find sometimes when it's like really raining and storming, it doesn't work quite well. It's because you have all this water between the satellite and your dish. Okay. Any questions about this? Does that make sense? So a lot of fascinating things and a lot of interesting career choices as it pertains to the infrastructure pieces of modern communication networks. Okay, so let me take a look at the time. It's 1:02. Okay, we have 13 minutes, so I'll call it 10 minutes. All right, so let's look at delay, loss, and throughput. So one of the key aspects that can either make or break the performance of a network is understanding the components that contribute to delay and to packet loss. Yes, we said that when packets arrive at a router or packet switch faster than they can leave, faster than they can transmit, they have to line up, and that leads to delay. If those buffers are full, well, then that packet gets, or some packet gets dropped, right? So delay is the waiting, and loss is the dropping of a packet. And so packets queue or wait for their turn to be transmitted out the link. And while the head of queue packet is being transmitted, the others that are in line behind it have to wait, right? That leads to end-to-end delay. And so these packets that queue, they experience a delay. If there are freely available buffers, newly arriving packets, they line up in the queue in the order in which they have arrived. Now, if there's no free space left, they get dropped and you get loss. And so if you want to make an accounting for all of the sources of delay for a particular so-called node or packet switch or router, these four components are the processing delay, dproc, the queuing delay, the transmission delay, and the propagation delay. So it's going to be really, really important to know one from the other, but a lot of people, even in industry, confuse the transmission delay and the propagation delay. So I'm going to really stress those and the difference between the two. So the nodal processing delay, dproc, that deals with that analysis that each packet switch or router does on a packet. And that analysis includes checking it for errors, right? It has a process that we'll talk about later for checking for errors. Did some bit get changed? Now, when you have interference in a communication, what interference is the changing of bits. So now that packet has information that's different from what the original sender intended. Now, if you're in a banking application, right, and you change bits in a number, right, 0111 is 7, but if you change that to 10, add an additional 1 and have it 1111, that's now 15. So now instead of some business transaction, instead of sending $7,000, you sent $15,000. There's a problem, right? And so one of the things that the routers do or the nodes do is to check for errors. The other thing deals with the forwarding table that we talked about before. It checks the address information and then decides through lookup in the forwarding table out which outgoing link that particular packet should be transmitted one bit at a time. And all of that takes time, and typically it's on the order of less than a millisecond. In modern routers, all of this is done in silicon. It's burned in custom hardware, and that's why you pay a lot of money for high-speed routers. You'll pay tens of thousands of dollars. So that's the processing delay. Now we have the queuing delay. Now the queuing delay corresponds to this idea that packets that are not at the head of the line have to wait to be transmitted. And so that waiting takes time. That waiting is called your queuing delay. So it's the time waiting at the output link for its turn at the head of the queue in order to be transmitted out of some link. And it depends on the congestion level of the router, where congestion is the amount of packets that are stuffing or waiting in that queue. If it's highly congested, your router queues are going to be relatively full. If it's lightly congested, your router buffers are going to be relatively empty. Okay? All right. So now we also have transmission delay and propagation delay. And I'm going to end with this and start back up on Thursday with this. And I really want to stress the difference. Transmission delay is governed by two things. The packet length in bits, and you have to remember it's bits with a lowercase b, and the transmission rate, which is bits per second or bytes per second. And please make sure you pay attention to whether it's lowercase b, bits, or uppercase B, bytes. Now, of course, when you transmit, it means to take the individual bits of the packet and to turn it into some signal that you can send down the link. If you are sending down a fiber optic strand, you'd have one frequency pulse, maybe 10 pulses a second for a 1 bit, and then you'd have another frequency pulse, maybe 5 pulses per second for a 0 bit. So you take the first bit, oh, it's a 1. Boom, boom, boom. Oh, it's a 0, the next bit, and then you encode that. Now, I just made up 10 pulses a second, 5 pulses a second, but you're pulsing at different rates to represent a 1 bit or 0 bit. So to transmit is to encode a 1 or 0 bit in a packet read sequentially into a form that you can send it down the wire. Now, if you're dealing with a copper wire, a 1 bit is 5 volts, and a 0 bit is, I think it's less than 2 volts, right? And so when you transmit, it takes time to read each of those bits, convert it into some form of energy that you can then send down some physical medium. And the time it takes to do that is called your transmission delay. Okay? All right. Propagation delay depends on two things. It depends on the length, physical length of the physical link, right? How far you have to go across some medium. And it also depends on the propagation speed. Now, the propagation delay is the length divided by the speed. And what the propagation delay corresponds to is now once your 1 bit has been encoded into a form that you can send down the link. Maybe it's a pulse of light at a certain frequency. Maybe it's a change from 2 volts to 5 volts going down some copper wire. The physical speed at which it takes, or the amount of time it takes for that energy to go down that physical link to the other side, that's called the propagation delay, right? The two are very, very different, and a lot of people, even professionals, will confuse this. And so propagation delay and transmission delay are very different. Transmission talks about the time it takes to encode those 1s and 0 bits, because you have to read them read the first bit. Say you have 10 bits, you have to read each one of these 10 bits and encode them, right? The time it takes to read and encode those 10 bits, that's transmission. Once a bit, 5 volts, how long does it take 5 volts to go down the wire to the other side? That's propagation, right? So it's really, really important, and I'll stress it again, to know the difference between the two. right? Okay. Any questions about this? Does that make sense? Okay, so with that, we'll end there, and I'll just say that the four components that describe the delay associated with a packet switch or a node, and the reason why it's called a node is because you represent this mathematically as a graph. The nodes are the routers, and the edges in the graph are the communication links, whether they're wired or wireless. And so the four components are the processing delay, the queuing delay, the transmission delay, and the propagation delay. Okay? All right, so I'll end there, and I will see you on Thursday. I'll also change the due date for one more day on the project assignment. So please look out for that on the Blackboard. I'll see you on Thursday.